about half of us here, but I do want to get started. So, accumulation from rate of change, that's what we did, right? We started um, prior to your last test, we started from a rate of change, came up with an approximate rate function, and generated some sort of accumulation, either approximate with that sum or, as we were talking about on Tuesday, in exact form using integral notation. So what our goal is going to be over the next 5 or 6 weeks, 5 weeks I think, until your test 2, not the mastery test, till test 2, is to figure out how this process works the other way around and the things we can do starting from accumulation and getting rate of change. So getting rate of change from accumulation functions, which algebraically is a lot easier, but doesn't really work unless we know some tricks from what we were doing the other direction. So what we were doing before, again, as I said, we were starting from an exact rate of change function and made an approximate rate of change function out of that to kind of visualize using just some of the values that were indicated, some of the rates that are indicated by the rate function, the exact rate function, every so often, using them for intervals of with delta x, and then measuring an amount of accumulation for each interval and appending those together so that we can model how much accumulation has happened by any value of x past our starting point, 0 or otherwise, lowercase a. But the expression to write our amount of exact accumulation just indicates we're doing that same process, but visualizing using all of the values of the rate function, making them infinitesimally small intervals so that we can use like every single point, if you can imagine, like if they're individuals sitting next to one another, using all of the rate function values to generate accumulation more precisely. So to get from one to the other, we use an integral, but going in the reverse direction, we're going to use some of the same steps. We're going to think about reversing the process we were just doing to come up with a way to think about making a rate function from an accumulation function. But we actually did this already a little bit. If you remember, we talked about Usain Bolt, and we had his distance from the starting line for the 9 point whatever seconds it was that it took him to run 100 meters. And we could estimate his speed at any moment during the race just by zooming in and computing a slope, right? A change in distance and change in time, so that dy and dx over small intervals tells us about the ratio of distance to time that varied within that moment, and then we can state that as a speed or a velocity for that moment. So it's a rate function value for a single moment. Now, we'd like to be able to do that for all of the moments, so we can do numerical computations kind of one at a time, but what we'd like to do is come up with a, how do we do this kind of more in general. So same way though, we can think about getting approximate intervals by using, small, every so often I'm going to divide this up and recalculate a rate of change, that dy per dx, whether it's speed or something else. And then just imagine those moments getting smaller and smaller until what I have is considered to be exact rate of change for any moment that I want. So exact accumulation functions sounds like just the term is a general term, so we can use it for all situations. So it sounds kind of like, what's an accumulation function? Well, so the distance that we talked about, Usain Bolt running, that would be one. You've been dealing with these since forever ago. Whenever you're trying to measure the amount of something, you can think of that as an accumulation function, because that amount generates over some change in an independent variable, whether it's time or not. It doesn't have to be related to time at all. So even things like geometry, if I were thinking about area as this is not a picture of y equals x squared, this is a picture of a square. But as the side length increases, the area increases. So I could talk about how the side length impacts the rate at which the area increases, or the relative rates of area increase to side length increase. But this area function measures an amount of something that you can visualize in this square. But You know, as the side lengths get larger, I have more area. Like I said, this isn't a graph of a parabola, obviously. But since it is an area that accumulates, I should be able to write it, as we were talking about on Tuesday, as this exact accumulation due to some rate. The only thing is I just don't know what this rate is, like what formula would go in that spot. But that's okay. I know that if I could find this rate function, I could express area as the accumulation of that. 0 would be a natural place to start for area of a square. You don't have to. We could start with the area of a square with side length 2 plus all of the stuff that accumulates after that. But this is just be starting with a square length, side length of 0, and accumulating at some rate or another. We just don't happen to know what it is until length x. Or same with the sphere, if you want to think about three-dimensional stuff. If I imagine the volume of a sphere being accumulating as the radius grows, that's the only dimension that we typically measure for sphere volume. You could do it based on circumference or something like that, but easiest measurement that's usually used in volume of sphere formulas is something about the radius length, diameter, either one. But if I think about how that generates, like, well, every time the radius increases by a little bit, I'm going to get a larger volume. And I know what the formula is for volume from geometry class, but how do I describe the rate at which that occurs? Because we could also, you know, volume, we maybe know this formula, maybe you forgot that formula, but 4/3 pi times x cubed if x is the length of the radius. But I should also be able to express it, like I said, using integral notation. If I knew the rate of change, the rate that relates the relative changes of the volume and the radius length, I could also express this in open form with that rate function here as I let t take on all the values from 0 to x. This would generate a formula that gives me volume of a sphere with radius x. So the thing is that we'd like to be able to express these rate functions, not only because that gives us a second way to express things like volume or area, but because it also allows us to do other things. Some of the things we're going to be talking about a little bit later after your mastery test are some applications of what if I know all these rates, if I can find how these rates are related to one another, how, like, maybe not just radius and volume here, but maybe it's happening like it did in this as an animation, something that happens over time. So maybe I'm talking about the radius increasing at a 0.1 centimeter per second. How fast is the volume increasing? Well, I know the volume and the radius have a related rate of change because I know that there's some rate that relates those. When one increases, the other increases somehow. That should be predictable because there's a nice formula for how one's related to the other. So if the radius is increasing regularly over time, then the volume should be increasing somehow regularly over time also, just not necessarily at the same speed. Like if I say the radius increases by 0.1 centimeter per second, the volume isn't going to increase by 0.1 centimeter per second because that's not even the right units, but it should be increasing. I should be able to find out how fast it's increasing in cubic centimeters maybe per second. And it's just because the radius and the volume are related to one another that one causes the other to change, you could say, independent and dependent variables. And so the rate of change, the relative rate between them, is something that we'd like to know about. Not just spheres, but like lots of different relationships. So spheres and squares are just simple examples that are easier to picture. But in any case, this idea of accumulation function, which sounds like a bizarre concept, it's just a catch-all term to cover all these sorts of things, from things like area and volume that are maybe geometric concepts to the things like, you know, like Usain Bolt distance that he's traveled in the race, or anything, in fact. Number of people that live in a country accumulates over time, can go up and down, so de-accumulate if you want. Any sort of function that measures an amount of something can be considered to be an accumulation function. So in any case, as I was saying, the only issue right now is we'd like to know about this rate function, not only so that we can describe that rate and solve problems with that, but also that gives us another way to express the amount functions or the total accumulation functions, like these volumes or distances. It gives us a second way to express them, because the more ways you have to express something, the more situations in which you'll be able to use that something, because you might have to combine it with other things where it doesn't meld well in its other form. So we're going to figure out a way to find these rate of change functions, or these ratio functions, how the volume changes with respect to the radius, or the area of a square changes with respect to the side length. Because if we can figure out those, we can kind of build on this. Now, there are going to be some patterns that arise, because we're actually going to be not just expressing them with long, complicated sums. The algebra for this half of the problem, this going the other direction, is a lot easier. We'll actually be able to express these directly in closed form, in nice normal like polynomials and logarithms and things like that. It just takes a little bit of work to see what these patterns are and how they're related to one another. So in any case, let's go back to the area of a square. Now, instead of having a graph of a physical square this time, because this isn't actually, like x squared, I want to graph y equals x squared. And my goal is to figure out what the rate function is. So here's y equals x squared, standard parabola looking thing. So what I'd like to be able to describe is what the rate of growth, I could say in this one, is of y relative to x, so the rate of growth of the area relative to the side length increase. As x increases, the area increases. As the side length increases, the area increases. But before we get into this, this is an exact accumulation function, like the end result of what we were just working on. Think about going backwards in our process that we're using prior to our test. Think about what would an approximate accumulation function maybe look like. If this is the exact, what would something that's not as exact maybe look like? Kind of similar. How could we maybe make an approximate accumulation function? Because if I want to get to an approximate rate function and then an exact rate function, I want to start from this and then kind of work backward. So what did the approximate accumulation functions kind of look like? Would it be a whole bunch of horizontal line segments? Would it be like a bunch of dots? What did the approximate accumulations look like? Like the result of using the summation with relatively large delta x's. Remember, those were those kind of chunky corner functions, the piecewise linear. They're connected end to end, but not smooth curves, because we had over each interval of width delta x, we'd have one rate that we use, and so over each interval we'd have a straight line, but not necessarily horizontal unless the rate was 0. So thinking about this guy here, and let me just start up this dude, maybe. And of course it's going to play around for a little bit. All right. So I don't know what color I'm on. Let me make it not red. All right, so if I wanted to make an approximate accumulation function, kind of thinking backwards from this, it would be kind of more jagged. And maybe it'd be above, maybe below, but if I were just going to do something, well, let's say I draw a point here, and maybe it matched up here somehow. Maybe my approximate accumulation function have something to do with it. Maybe something like that. Or over the next interval, that would maybe go to, I'm just using 1 unit intervals, so really bad approximations. But if I had something like this, I mean, despite the fact that that's 1 unit wide, if I could draw slightly straighter lines, see, well, it's not exact, but it's actually not that bad, because this isn't a rapidly changing function, this y equals x squared. It's increasing and increasing more quickly. But I could say, oh, well, I've got one rate that I used for this first interval. So I just picked delta x equals 1. That's just, I pulled that out of my head. that wasn't anywhere stated on here. So if I use a delta x value of 1, say, oh, well then maybe an approximate accumulation function to be these two straight line segments if I go from 0 to 2, which is about all the farther I can go on this picture here. Which would mean my approximate accumulation function would only have two parts to it, right? So I'm just going to do piecewise function instead of trying to write a sum here. But over this first interval, I've got a slope of, let's see, goes from 0, 0 to, well, at 1, I know what the exact y value is. It's 1 squared, so 1. Or during the second interval, I go from 1, 1 to 2, 4. Right? I know that at x equals 2, the exact y value is 4. Now this isn't precisely how our approximate accumulations matched relative to our exact accumulations when we were going the other direction. They were usually like either underestimates or overestimates, and the smaller delta x got, the closer it got, but they're this sort of thing. Right? So if you can just, well, we're going the other direction, we're going to have to do something different. So let's just make our line segments connect to the curve that we have. And over this first interval, if I want to write the equation of this line, I start at 0. So doing it the kind of generic way, start at 0 and then increase at a rate of, let's see, the rate for this section would be a ratio of 1 to 1. So I'm going up at a rate of 1 for every change in x that I have past 0. This is for x between 0 and 1. So that's the equation of this line segment here. Well, this dot then is actually a part of the next line segment, but this next line segment has a different slope, 4 minus 1 over 2 minus 1. The rate of change that I'm going to use is 3. 4 minus 1 over 2 minus 1, just change in y over change in x. But I start at this y initial plus m dx, however far x goes past 1 for this next section, up to 2, and then at 2 I'd continue on with a different function. But these two pieces model the two line segments, imagining I can draw straight lines, the two line segments that we have here. So that's an approximate rate function. Now, piecewise functions are tedious to write. Good thing is, our goal is not to write the accumulation function, our goal is to write the rate. Guess how much of that is the rate? Not very much. 1 and 3. So I can write that approximate rate function, or the approximate accumulation function out, but our goal was to write an approximate and then exact rate function. Well, this is the easy part, and I don't, as you can tell, need all of this stuff to write this rate function. I just say, oh, well, all I need is, it was 1 in the first interval and then 3 in the second interval. That's all. So I've got between, let's see, 0 and 1, and then it changes to 3 if my x is between 1 and 2. So nice to know, this is how we did this before, but the good thing about working from accumulation to rate, we actually need less information. When we're working from rate to accumulation, we talked about the fact that, well, I don't know really where I'm starting from. So all I can generate is this net accumulation. I don't know how much sand there was on the scale to start with. I don't know how many people there were in this country in 1900 or whatever the accumulation function was about. All we could measure was net change from some starting point in time in whatever our independent variable was. But when we're looking at rate, we don't care about the actual y values at all. We only we care about the change in them, the variation that they encounter as the independent variable increases. So this same graph could be moved to someplace entirely different, y equals x squared plus 7. The rate function would be exactly the same. If I move it left and right, it's going to be over different x intervals. But in any case, finding this rate function, we did that. We kind of skipped over. You can actually skip over this step. Just realize that we don't have to write the equation of those two lines. We just actually are working on finding their slopes. Now, is this a very good rate description? if I were going to graph that rate function, graph y equals r of x, what I've just had, let's see, it has a rate of 1 from the beginning up through x equals 1. And then through x equals 2, I go up to 3 and do the same thing. Ooh, very exciting. There must be something that's slightly better. I could do this over more intervals, right? And just do the same sort of change in y or change in x. And we could do this over and over, and it's not very hard, especially with a function like x squared, to find the xy coordinates of any points and find the steepnesses between them. But unless we do a whole bunch of them, we're not going to have a very nice rate function. And it would be nice if we could express this, instead of doing all the individual computations, if we could write a formula that expresses how to do these computations in general. So, well, pick your interval width, what points do you need, and then how do you express that in general for any interval where I know where my intervals are starting from. So kind of getting back to doing this a little bit more rapidly than when we went the other way around, but if I can figure out how to express doing this sort of thing in general for any delta x, starting from any spot, I started from 0 here, then we can make delta x smaller and we can make a better approximation. So that's not too bad. But let me get back to, we already talked about, not going to be like that. So our exact accumulation, or approximate accumulation, is going to be piecewise linear. And the way that we can do this is to, and so this is what I already drew, draw line segments between points on the curve and then compute the constant rates of change that pertain to each interval. So if we did smaller intervals, so this is with delta x equals 1/2. You can see that there's not much space. You can hardly see between the blue and the red. So it's a pretty good approximation, even when it's just delta x equals 1/2, which is relatively large compared to, thinking about things we were doing before, like 0.001. So the constant rate of change over each interval, though, we could compute. I don't want to compute all of those. That's number crunchy sort of things. But it's just change in y over change in x. Easy enough to do if we want to. But we'd like to be able to express how to do that in general. So, sorry, I just kind of went over this already a little bit on the last page. So the red curve was the exact accumulation, and this blue piecewise linear function, that's the approximate accumulation. That's what's represented here. And I took the x and y values out. Let's just talk about this in general. Now I know this is really still the same picture, just blown up here. But suppose that I want to just express a general. So I don't have like f of x equals x squared. This is just generic f of x and a generic piecewise linear approximate accumulation that matches up with it. So for every x value, I want the associated constant rate. So let's say I'm talking about x here. If I want to express an approximate rate function for any value of x, I need to be able to just talk about, well, for any current value of x, how do I find the rate of change if the approximation looks like this? Well, if I can see it in there, I can say, oh, well, I'd use this point and that point. But thinking about, sorry, click a couple times, there we go. So if I see, this isn't like necessarily first interval, second interval, whatever. So just think about this as a general interval. X is in the middle of some interval. I want to know the constant rate that would pertain to it. So if this is x here, and this is the interval beginning immediately to the left of x, what do I call the x coordinate at that spot? If it's at the beginning of the interval that x is in, yep, this is left of x. So the x coordinate here is left of x. Now, talked about defining left of x. We said, okay, so that's a plus x minus all that stuff. But short notation, that's left of x. What would I call the y coordinate at that spot? Not like y equals x squared, but just using f as the name of the function. The y coordinate that corresponds to this x coordinate? Yeah, f of left of x. So a composition of functions. I find left of x, and then I substitute it into function f. So this would be a general point that's at the left end of the interval that x is in. Whatever interval x is in, it starts at left of x and ends at, well, what x value would be the right end of the interval? I don't want to call it right of x. How else could I express that? Using just notation, thinking about what we did last unit. What about delta x? Delta x is how far apart those are. So if this is left of x, here's x in the middle. What's the x coordinate at the end of the interval? It's more than left of x, right? It's larger. It's delta x larger. Left of x plus whatever delta x is. So if this was 1 and this was 2, this is, oh, x is 1 point something. It's in the middle of this interval that goes from 1 to 2. If it was delta x equals 1 like we did the first time around. If this was, some other function entirely, I don't know what these are necessarily. This corresponds to what we talked about. But if these intervals are delta x units wide, the interval that any x is currently in begins at x equals left of x and ends delta x units later. So I can just add that on. Well, so that means I also know, although it's a little bit tedious, an xy pair for this point. It would be left of x plus delta x, comma, f of all that same stuff, right? F of left of x plus delta x. Oops, I've got parentheses. So messy notation, but I can express the beginning and the end coordinate points for any x value in general using our notation left that we introduced. I know left depends on what's a, the starting value of accumulation, and what's delta x. A plus x minus a over delta x floor, all times delta x. That's what left of x is. But let's write it the short way so that we can just express the beginning and the end of any interval containing current value of x as being between those 2 points. So guess how I find, in general, an expression for the rate. If I can express the endpoints of any general interval like this, for any value of x, I can compute a rate then. Change in y over change in x. Now, change in x part's easy. Over this, between those 2 points, how much did x change? What's the variation in x? Delta x. All right, so the denominator of this rate is easy. It's delta x. The numerator is, well, lovely expressions. y2 minus y1, if you want to think about that. But the variation in the y coordinate, y final minus y initial over that interval, this lovely expression minus that one. And they don't reduce at all. It's f of one chunk minus f of another chunk. You can't subtract the inner parts, unfortunately. So it's a little bit messy, but for any general x then, we can express this approximate rate. Now just realize, if I drew x here versus a little bit to the right versus a little bit to the left, I'd have the exact same rate. But that matches up with what we talked about before, having one rate that lasts for a little while. And then when I jump into a new interval, maybe that's when I calculate a new rate, and that lasts for a little while. So there we are. This is the neater version of what I just had. But we have left of x and f of left of x, and then left of x plus delta x and f of that same thing as the endpoints of the interval that any x is currently in. Can you put your phone down, please? So our rate function would then be given by this expression, y final minus y initial over, well, same with the x's, but I know what the variation in x is. The interval width was delta x. But you can also do left of x plus delta x minus left of x. That leaves just delta x. So here's an approximate rate function. And how could I make my approximate rate function better? Make delta x smaller. So don't do this. Sorry, I forgot to take that out. I don't want you to worry about writing the approximate function, the approximate accumulation function a, because you know what? We don't need all of that. All we need out of it is the rates. But if you wanted to express it generically, I can say y initial plus m, that's approximate rate function, dx. We could write that. But the thing is, if our goal is to find the approximate rate function, we've already got it. It's just this. I don't need all of the surrounding parts. But similarly to how this expresses the rate for any value of x, the approximate rate for any x in any interval, this expresses the approximate accumulation for any x in any interval. Because this would be the y initial for that interval plus our rate that we just wrote above times x minus, well, however far it is into its interval, x minus left of x minus the beginning of the interval. So we can express it in one line instead of piecewise, but the thing is we don't actually need to write it, which is actually, that's nice. So let's talk about, sorry, clear this off of here. Where is this? Oh, graphing calculator. All right, so I'm going to pass out a sheet in a moment, and I'm going to give you a chance to play around with this. But suppose that this is my function f here. And as x increases, so this is my exact accumulation function that I'm looking at. As x increases, I can see y increases. First it increases rapidly from around the origin, and then increases more and more slowly. So if I were thinking about trying to generate an approximate rate function, I could think about, well, let me make some intervals, and I have mine about 0.2. Let me make some intervals that are 0.2 units long, and beyond the first interval, you can hardly tell the difference. Now, let me just, for demonstration purposes, if I had larger delta x values, it's even like delta x is still even too large to fit on there. Only that first interval where the y relative to x is changing really rapidly, can you even tell the difference from this approximate accumulation from the exact accumulation f? So whether I use 0.2 or something, here, let's see if I can get this to, I'll just leave it at 0.4, that's easy enough. I can see this approximate accumulation for the first interval, and then after that it just kind of matches up. It's so close to the exact that I can hardly tell it apart. So if I wanted to draw a rate function, I know that the rate function is just f of left of x plus delta x minus f of left of x all over delta x. It would look, let's see if I can get this over farther. No. Let me scoot this. There we go. I don't know how that got over that far. So I've got my rate function. It's still off the screen for you. There we go. And this is a poor approximation, agreed? Using these rates for very long times. In reality, my rate should be changing all the time. So if I make smaller delta x values, like closer to 0.2, all right, that gives me a higher steepness for that first interval, a higher rate for the first interval, but they still drop down. And you can maybe imagine, oh, as delta x gets smaller, these planks that I have on the left would kind of start to blend together. They'd be, instead of the impossible to go down without falling over staircase, into something that more resembles, okay, maybe you could step down this step function. Like I have maybe h around 0.1 or so. Now the first step is still really high, but these others, okay, I can see how these are kind of forming a pattern now instead of just being a few spots here and there. And the smaller h gets, the closer they get together. Left to right. Now right near the y-axis there's still huge jumps because the steepness here was incredibly large if I'm looking only extremely close to the origin. And then as I go out just a little bit it drops down suddenly. But now at least this looks like, all right, maybe they're little tiny steps, so in that sense they're kind of hard to go down. But maybe it's starting to look like something you would slide down. So when I make h, well, this is the name of my slider is h up here, but it's our delta x, our interval width. When I make that incredibly small, these start to form this pattern where I can imagine a curve that connects them all. Now here's the problem. When we were going the other direction, we started with a nice smooth rate curve, and we're able to break it down into chunks, and then we can write a piecewise function that connects them together for our approximate accumulation, and then that smooths out, but it's connected all the time. Unfortunately, there's not a way to reconnect these by making the intervals smaller. They don't end up running into one another. We can't make a continuous function out of it going this direction, so we're going to have to do something else. But before we do something else, I'm going to leave this running up here, and I've got a worksheet related to what we were just talking about. So on the front side, you'll see two different pictures. What I'd like you to do is, well, the instructions are on there. The first one is called the net accumulation, just because it starts at 0. The other one's called the total accumulation, because it doesn't. But those are exact functions. And I'd like you to just sketch, not do any computation, sketch what an approximate accumulation would look like. And these instructions are all on paper. And then just, without really doing computations, just relative size-wise, sketch on the other set of axes what an approximate rate function would probably look like. And then estimate what the exact rate function might look like based on that. Just kind of thinking about the trends in the steepness. So just thinking about these visually. There's a fill in the blank sentence first. But then there's two different graphs with accumulation. One starts at 0, so you can call it net or total. The other one doesn't start at 0, so just be a total amount or total accumulation. But just think about what an approximate accumulation would look like connecting some dots. Nope. Thanks. I'll give you a couple minutes to think about these. Don't do any computations, like I said, just relative sizes. So don't worry about there's no y values on the graphs. So don't worry about how high, how low, just positive, negative, less negative, you know. And I think, hold on just a sec. I think I have this too. I just don't want to open up weird stuff. There we go. So I'm gonna draw up here, but I'll let you do it on your own first. Okay. so just big picture-wise, at the top. Right now we're starting with exact accumulation functions and generating or sketching approximate accumulation functions from them. We don't actually have to write out their formula because our goal is to get, well, to an approximate rate function. And ideally, after we get an approximate rate function, we'd like to get an exact rate function somehow or another. Like I said, there's a little bit of a hiccup. You can make something discontinuous, but it's hard to put that same thing back together. So let's take a look at the idea of creating the sequence of things. So starting from an exact accumulation, either net or total, we're going to make approximate accumulation functions, those piecewise linear functions, somehow. And then from those, create approximate rate functions, one value for each interval. And then the idea is if we make the intervals smaller, we can come up with some exact rate function. So just thinking about what these could kind of look like. So with this first example here, if I'm using 0.2 as my interval width, that means I go from 0 to 0.2 for my first interval, 0.2 to 0.4, 0.4 to 0.6, and so forth. I'll just stop at 1 since that's the last full interval. But for each interval, we'd approximate the exact accumulation by, and this hardly even looks like a straight line, by making a straight line that connects the dots. So for each of these intervals, I'd have one single rate. So going from 0 to 0.2, I can see I've got a large positive rate, and then a smaller positive rate, then a smaller positive rate, and then a slightly negative rate, and then a more negative rate. So if I were going to sketch something like that, there'd be 5 steps to my step function. The first 3 would have to have positive values, but the first one would maybe be like the largest positive value, then a lower positive value, then a lower positive value. This one's just hardly positive, so maybe I'll even draw it down here. Now if I wanted to be a little bit more precise about this, we were doing them this way, right? So closed on the left, open on the right, and so forth. Like our intervals 0.4 through, but not including 0.6. These last 2 intervals would have negative rates. The y value, the amount of accumulation, decreases through both of those 2 intervals. So slightly negative and then more negative. So maybe like this. And again, the exact y values for these don't really matter, just the positives versus negatives is important. And the fact that it's a decreasing sequence of rates throughout. So I've got a large positive, lower, lower, and then so low that it becomes negative and then more negative. So I've got a decreasing sequence of rates. So if I wanted to make smaller intervals and make a more precise rate function, say, oh, well, this rate function, it'd probably be something like, starts at a high positive number, probably higher than the slope of this, and then go down, maybe something like that. Maybe my exact rate function, if I can imagine making a whole bunch of little steps, my rate seems to be closest to 0, changing from positive to negative by going through 0 right around 0.6. So, right around this area, I should have a rate near 0. Because it's not quite increasing and not quite decreasing, it's kind of turning around. So in terms of matching up, where would my exact rate function maybe hit 0? Right around 0.6, maybe a little to the right, maybe a little to the left, but this seems kind of reasonable then. If I were going to estimate what this looks like. Now this might be a straight line going down, it might be a curve going down, I don't really know. I don't have a function, I don't have precise y values, I don't have any y values at all, even over here. So, but what I do know is positive versus negative rates of change based on the look of this graph. So the thing is that getting from the steps to something that's smooth and connected, that's the kind of tricky part. So we're going to have to work out a way to fix that problem. But let's look at the other graph on the front. There we go. So this graph, its rate values are, in the part we can see, all negative. Right? So looking at this from left to right, this graph is always going downhill. So if this is my amount of something, it's always de-accumulating, if you want to think of it that way. If I use intervals of width 0.2, looks like maybe from there to there, I'd have a very negative first rate relative to the sizes of the other rates, but all would be something with a negative rate of change, becoming less negative as I go on this time. So closer to 0, I guess, but this doesn't flatten out to a horizontal line that would have rate of change or dy over dx equal to 0. And I apologize for my inability to draw straight lines here. But we've got negative rate and then a less negative, as in closer to 0, closer to 0, closer to 0, closer to 0. So if I were going to sketch something, maybe, I don't know, maybe my first rate is down here. And then it becomes less negative and less negative and less negative. No reason to have whole number values or whole grid values, but just, you know, something like this would be appropriate for an estimate. Where these last few are pretty similar rates to one another. So if I were trying to think of, well, what would an exact rate of change function maybe look like then? Well, at the beginning it would be, if I were using smaller intervals, I'd get a much steeper, like much more negative rate than what I did by connecting these that were 0.2 units apart. So it would probably be like, you know, off the screen negative down here, but it increases all the time, doesn't hit 0 in the visible range, but gets pretty close to it. So maybe something like this, or just kind of estimating what might this look like. So notice how it doesn't go through the endpoints of our intervals. That's because we're doing this from the other end. So our intervals, when we're using them before, we use the rate at we started from a rate function. We use the rate y value at the beginning of the interval and use that throughout. Well, I'm not using the rate value from here. I'm using the rate for the full interval, which in this case is going to be less negative, closer to 0, than the actual rate value is. So my approximate rate doesn't match up with the exact rate the same way it did when we were going the other way around. But that's okay. We're just doing something kind of similar. We're trying to reverse this process. We can't do the exact same things like in backwards and forward because just it doesn't work out that well. We have different pieces that we can compute from. But we can still generate the same ideas. So on the back side of this handout is actually the picture that I was showing up here before, the GC animation. It's that same shape, this one here. So we've talked about this already. If I do this exact rate function, or if I try to make an exact rate function, what I'd have to do is make this, well, I have it written here as h, but delta x, I try to make that delta x, that interval width, really small. This h is my slider name. So there's a reason I actually use this symbol h, and it's because we're going to do something else. So this delta x is the idea of start at a, and then every delta x units, we're going to start and stop a new interval. We're going to stop and start a new interval, whatever order I want those commands to be in. But the problem is the connecting. So when I have large intervals, I have this extremely, far apart step function sort of thing going on. It's not particularly close to being connected, but by making them smaller, they don't suddenly become connected. They just kind of generate the shape of something that's connected. What I actually need is a new formula that as x moves, even the smallest amount, I don't care what interval it is, I need the rate to just vary by a small amount also. And so we're gonna alter what we were doing. So like I was just saying, even what we're just doing, these steps don't match up with the exact rate function or the idea of the exact rate function the same way as when we're going through this process the other direction anyway. So let's just make a little bit of an alteration that'll help us with this continuity problem, because there's no way to make a piecewise constant function, a whole bunch of individual y values, all of a sudden into a formula that has like y values that connect. We can't make them connect to one another. So we need to have not separate intervals. So what we're going to do instead of what we've been doing is, here, I'm going to make h larger again. So instead of having this delta x where I have these fixed intervals, and when I move from one interval to the next, I suddenly change values then, what I need is, as x increases, for the rate to always be being recalculated anyway. And I'm going to do this with a large interval, but it doesn't actually matter the size of it. If I, instead of having, here, why is this showing up so large? I'm not quite sure. Instead of having beginnings and ends of intervals preset, if I just think, let me think of a general interval that's, I'm just going to call it h instead of delta x, so it doesn't get confused with it. Every interval is set at specific spots. If I let h float around with x, that is, wherever x is, I'm going to measure ahead of it by h units. And that gets me to the end of a new interval. And every time x changes by a little bit, my h is in the end of the interval is in a different spot. So I've got different intervals for every single x value. The nice part about that is they all connect to one another. Or what I mean by that is, if I'm going to estimate slopes over these intervals, oops, I kind of skipped one. There we go. This tangent line here, or the secant line rather, between these 2 points, that would be the rate that I'm calculating, the rate of change for this constant blue line here. So I can see, like, as x moves forward, the slope of this blue line is the slope that I'd be calculating all along, and it kind of blends from one high value at the beginning to a lower value to a lower value. So I can see, oh yeah, it smoothly changes from one to the next. I don't have these suddenly change to a new interval and something else happens. There aren't preset intervals. All I have instead of interval positions and lengths are just interval lengths without a specific position. The position is just x is the beginning and x plus h is the end for any value of x. So I don't have to worry about left of x and that nonsense. That actually makes it easier to write also. But what this means is, as x changes, I get this smooth connected set of values, because you can see this line here isn't keeping the same steepness for a while and then all of a sudden changing to a different angle. The second x moves even a little tiny bit, that line tilts, or the slope that we're calculating is the slope of this blue line in the right picture. Now, this is an approximation. So this is with h equals 0.4. I can make h smaller and get better approximations. But these approximations have approximate rate functions that aren't piecewise chunks or steps. These approximations are connected functions that have a fairly simple definition to them. We just imagine h to be a small number. And then this is just change in y over change in x for every value of x that has a different value. But this, for any function f, is something that is a nice, nearly closed form, kind of regular looking addition, subtraction, multiplication, logarithms sort of function. So there's different ways we can go about simplifying, but that part's just algebra. So thinking about this blue that I have here, this is still just an approximate rate function. The exact rate function would be this red one. That's if h gets exceedingly small. With large values of h, with large positions, like large intervals between our actual x value and where we're calculating the slope to, h units later, we get approximate rate functions, but they're the same sort. They're connected. As I make h smaller, and this is not something that's easy to draw on paper because you have all these, you don't have separate intervals where you can just compute separate slopes. That's why I didn't have you draw anything with this one. just for every h value, we have a different similar rate function that occurs. And when h gets smaller, it gets closer and closer, hones in on one particular position, which is the same one that those step functions, all those little pieces, were going up to. But the problem with that was the delta x, no matter what that delta x is, we have two different x values that we're using each time, and neither of them is the actual x value in question. This one only has two x values, and one is our x value in question. So this is a simpler function in that sense. And this is the function that we're going to use to describe approximate rate of change for f of x, with this h just indicating how am I getting this approximation. So if you were doing this numerically, I could get different numerical rates for every value of h. If I want to get a function, what I want to do is imagine h becoming essentially 0, infinitesimally small, and picture-wise, what happens when h gets exceedingly small is that this narrows in on one particular picture, but the algebra of this is actually a lot easier than the algebra of those approximate accumulation functions we were dealing with before. For instance, let me just open up a blank something or another. I'm just going to open up a blank GC window, not to calculate on it, but just to write on it, because it's white. So let me write in something that isn't red. So we had that function for the area of a square. I'll just call it f. F of x equals x squared. So this gave us area of a square, gives us lots of other potential things, but in that context, as the side length increases, the area increases. And so our rate functions, they are near 0 here, and then they become positive and greater as x increases, meaning the rate at which the area increases grows as the side length becomes longer and longer. Now, the formula that was on that GC file said our rate function can be computed by doing f of x plus h for any value of h minus f of x and divide by h. This would give us a function in x for any value of h. And so if this is our expression here, f of x plus h, just keep in mind is x plus h squared, right? Just that's what that literally means. If I have a formula, a function rule for f of x, then I can write out a function rule for f of x plus h also. And so this approximate rate function, which visually is the approximate steepness of this, or the slope of this curve at various points, could be defined by, well, x plus h squared, f of x plus h that is, minus x squared all over h. And so if I said, okay, so if h is 0.2 and I'm looking at x equals 4, what's the rate value? Well, that's great, but nobody really cares if h is 0.2. What I'd like to know is, how do I make an exact rate function? To get an exact rate function, what I need to do is imagine h becoming essentially 0. So you'll see this notation, or sometimes the approximately equal sign. Either of those, sometimes this has 3 lines. H approximately 0. So imagine h becoming approximately 0. What does that tell us? Well, if it is 0, then this is nonsense because this is division by 0. And it'd be x squared minus x squared over 0. That's even more nonsense. So that's not helpful. So don't imagine it equals 0. Imagine it's approximately 0. Well, meaning don't plug in a number for it, but if we simplify this expression just using some algebra, i.e. square the binomial, there's some simplification that can happen, and in the simplified forms, it doesn't matter whether h is 0 or 7 or 19, we can evaluate it all just as easily. So let's do some algebra here. Meaning, I could subtract this numerator, if I were to work this out, would have an x squared in the beginning minus another x squared. Those would go away. I just have to write this out so I can combine the like terms. So quick algebra review, x plus h times x plus h, just remember, is not x squared plus h squared. Those two are in there, but there's other stuff, right? FOIL, or whatever you want to call it. I have x squared, I have an xh and another xh, so two of them, and an h squared. That's this first term, and then there's a x squared, and this is all over h. This is still my approximate rate function. But from this form, you can see the algebra is going to help us clean this up a little bit. Those two terms are like terms, subtract one another out, disappear, whatever. Everything remaining has h's in it, which is actually good, because the numerator, 2xh minus h squared, that can then be simplified by dividing out a factor of h. Remember, you can't just like start crossing stuff out, you have to factor to reduce. So, as I said, a little fun with algebra today. So, some more algebra. I'm going to factor out an h from the numerator so that I can do my other algebra thing. Favorite thing about fractions, cancel common factors. So this rate function, just doing two varieties of algebra, squaring a binomial and factoring to reduce, comes out to be 2x minus h. This is an approximate rate function, right? Question? Oh, yeah, sorry. I'm like, what? I was looking in the wrong spot. Yes, you're correct. Let me fix that. That's plus h squared. Plus h squared. That's plus h then. All right, so this is my approximate rate function still, right? This is for any value of h and any value of x, I can find an approximate rate value. Now, my goal would be to find an exact rate function, which, if I imagine h is essentially 0, which now is pretty easy to do in the simplified form, say, oh, well, if h is essentially 0, then this is essentially 2x, right? And the closer h gets to 0, the closer that expression gets to just being 2x. And what that means is that my exact rate of change function is 2x, not because I just substituted in h equals 0, but because this expression, unlike this one up above, the smaller h gets, the closer it gets to being this, which what that means is this curve here, visually speaking, this tells me about the steepness of it. For any value of x equals 1.2. Well, at 1.2, in that moment, the rate of change is 2 times 1.2. This rate is about 2.4, meaning if I were going to draw a line with a slope of 2.4 that goes through this, it would seem to be the same steepness as my parabola here. So this is an approximate rate of change in simplified form, but having it simplified allows us to, because this h is now just a tagged on little plus, it allows us to use any value of h we want equally well, as small or as great. And you can see that the smaller h gets, that gets closer and closer to just being the same as the linear function 2x. 2x plus smaller and smaller things is essentially 2x. So from f of x equals x squared, we can get an exact rate of change function 2x. And similarly, I'm going to clear this off. We can do the same thing with, let me use a big eraser. What if I have the volume of a sphere function instead? if I had my volume is 4/3 pi x cubed. Volume is a function of x. So it still kind of looks like that in the first quadrant. But if I want to find the rate of change of function v, I'd need to do this. Now it's going to be a little bit messier than with just x squared, but same idea holds. It involves the same sorts of additional algebra. We're going to do some, well, cubing a binomial and so forth. Getting rid of the old numbers and keeping the new ones. All right, so if my approximate rate function then, let's see, if we have v of x is this, then I need v of x plus h would be the second part for the numerator I'd need. So that would just be 4/3 pi times x plus h cubed. So I've got this and that I'd need to compare the values of. And again, what that is on this curve, finding steepness between any 2 points that are h units apart and expressing that generally. So if this is x, and this is x plus h, and this is v of x now, 4/3 pi x cubed, I want to express the slope between those two, and then I can imagine h becoming smaller after I do some algebra, because especially with polynomials, by doing this sort of simplification, working out the terms separately, you can do some, canceling of like terms and factor reduce sorts of things. And there's nice patterns that emerge because it is math and that's how it works. But let's see, so I'd have this 4/3 pi times x plus h cubed minus 4/3 pi times x cubed all over h. And I'm going to do some algebra with this. Now, there's that 4/3 pi in both terms of the numerator. If I want to factor that out now and not deal with it, we can do that. So just as a variation on the algebra we did last time, 4/3 pi times, think about it like over 1, times our fraction, x plus h cubed minus x cubed all over h. Would you agree that that would be the same as the rate function above? So if I were to multiply those together, I'd distribute in the numerator, and it would be the same. So this looks more like what we had last time. It's just this extra factor out here. We'll just tag it on later, multiply it on. Now x plus h cubed, not so fun, but hey, guess what? I'm actually on GC. So x plus h to the 3rd power. One of the things that GC can do is expand things. That's what it is. So instead of doing this manually, which you can do, maybe takes a minute, or if you remember like Pascal's triangle or binomial theorem, you can do it quickly. But that's just under the math menu. It says expand. And so I just highlighted my expression that I wanted expanded, and it does that multiplication for us. So hey, great. There's that. So that means this first portion has 4 terms to it, one of which is something that I'm going to subtract at the end. So let me just change colors here. So I've got my 4/3 pi. I'm not going to put it back over 1, but just multiply it onto this lovely fraction, where I've got x cubed, 3x squared h, 3xh squared, and then minus x cubed. In this, the terms without h all drop out. So you can see the same sort of simplification as last time. We can factor out an h from the terms. Oh, I forgot my x. I was thinking about, got an h cubed. I left out this guy. So I've got 3 terms remaining. They all have h in them. So I'm going to factor out this h, just to be with those guys, and then have remaining 3x squared plus 3xh plus h squared all over h, and reduce out. So overall, just recopying this to where there's more space to write, my approximate rate function, without a fraction involved with h in the denominator, I've got 4/3 pi times 3x squared plus 3xh plus h squared. Did I miss any terms? So obviously we could reduce some things with the 3's and some of the terms, but what we're really looking for is, well, what happens to this as I make h smaller and smaller? Well, it's a polynomial with some terms that involve h and some that don't, but just as factors. There's no h's in denominators anymore. So as h gets closer and closer to 0, these two terms do as well, right? 3x times h, if h is getting close to 0, no matter what x is, this is going to eventually turn into 0. This one's going to be getting closer and closer to 0. There isn't any x in it in the first place. So as h approaches 0, I'd have just 4/3 pi times 3x squared. And I'll just leave it as that. So this is our exact rate function then. And why I wanted to leave it as that, for comparison with when we had our quadratic function, x squared had a rate function that was 2x. This 4/3 pi x cubed has a rate function that's 4/3 pi times 3x squared. So this 4/3 pi is just kind of tagged on, but if you can see, the x squared part turns into a 2x. X cubed turns into a 3x squared. If you had to guess, going through very similar processes with an x to the 4th, any guesses as to what its rate function would have in it? Yeah, have an x cubed, and what about coefficient? 4. Yeah, we're going to talk about that on Tuesday next week. I'm going to have you read some stuff about patterns that arise in these, but these are not just magical weird things to do. They tell us about steepness or about rate of change. I will see you on Tuesday.